This is a debrief of the 2012 multiple choice no calculator section. So I'm going to go through these problems. If you're in my class, you have access to the work, and you'll notice that I have written a commentary for almost every question. So this video probably will be pretty short and pretty fast because I think most of the explanations are pretty good already. Whoops, sorry about that. Are already pretty good in the commentary. So let's just kind of roll through this. In number one, they want us to find the derivative of the given function. The most common mistake here that people make is not realizing that this is a product. This is x multiplied by sine x, and it's going to require the product rule. So when you do the product rule, you have the first times the derivative of the second plus the second times the derivative of the first, which is just 1 in this case, and then you have to look for your answer that matches up. So really easy for number one. In number two, we have a function f being given to us. That's an original function, and we want to know the intervals on which the function f is increasing. So to figure out where f is increasing, we need to figure out where the first derivative is positive. So step one is to take the first derivative, and then we're going to set the first derivative equal to 0 so that we can create a number line. So I subtracted or added 3x squared to both sides right here, and then I divided both sides by 3. Then I took the square root of both sides, and then I take my critical numbers of -10 and +10 and put them on a number line. I'm going to test a value in region 1, region 2, and region 3, and I'm substituting those, remember naming the number line is important, into the first derivative, and then I can see that the increasing interval is the one that is from -10 to 10, and so that's why I selected B. Number 3, pure memorization. You just have to recognize that this is that secant x tangent x is the derivative of a function that you know, and the antiderivative of secant x tangent x is secant x, because the derivative of secant x is secant x tangent x. So you can just go back and forth and check yourself on that. In problem number 4, we have an original function, f of x is equal to this function given, and we want to find the derivative at 1, so we're going to find the derivative of 7x, which is 7. The derivative of 3 is 0, and the derivative of ln of x is 1 over x. I'm going to substitute 1 in place of x here, and then simplify, and I get a value of 8. Easy peasy. You can not worry about that. Number 5, the graph of the given function f, this is f over here, f original, is given. Which of the following statements is false? So the limit as x approaches 2 of f of x exists. So when I approach from the left and I approach from the right, I am approaching a y value of 2. Remember, a limit is about what you approach, not what you actually reach, or the function value. So that is a true statement that the limit does exist. Letter B, the limit as x approaches 3 of f of x exists. So when we go towards 3 from the left, 3 from the right, we are approaching a y value of 5, so that is true. The limit as x approaches 3 does exist. When we go to the limit as x approaches 4, from the left, we're approaching a y value of a little bit less than 2. From the right, we are approaching a y value of 4. They do not agree. So this is the false statement, and once you get a false statement, you don't need to keep reading. They said which one of these is false, so it has to be C. Number 6, a particle moves along the x-axis. The velocity of the particle, so we're dealing here with velocity, is given, and the velocity is 6t minus t squared, and we want the total distance traveled from the particle. So this is the no calculator, so we're going to have to figure out, are there any places where this function has it goes below the x-axis? So we're going to start by, sorry guys, I got to shut this off. Give me 1 second here. So I'm going to start by figuring out where the velocity crosses the or intersects the x-axis. So I factored out the t. I set each factor equal to 0, so I got t equal to 0 and t equal to 6. Then I'm going to test out the regions to figure out where, the area is positive or negative. So I put those critical numbers on the number line of 0 and 6, and they're telling me only to go from 0 to 3. I find out that that region is all positive, so I don't have to make any breaks anywhere in the integration. So I'm going to accumulate the area from 0 to 3 underneath of 6t minus t squared. This is a reverse power rule. It's basic anti-differentiation. Be careful with your arithmetic and substitution and choose your answer. And again, if you're in my class, you can go and look at these answers and read the commentaries. You don't necessarily have to watch the video to get the most out of this. Number 7, we're given a function y original, and we're trying to find y prime, the first derivative. So this is a chain rule problem, as you can see. So the outside function that we're going to deal with is the power. So we're going to do the power rule. So the 5 goes in front. We're going to decrease the power by 1, and we're going to leave the inside alone. Then we're going to take the derivative of the inside, and the derivative of x cubed is 3x squared, and the derivative of negative cosine x is sine x. So remember, this is one that you could easily select the wrong answer. When you take the derivative of sine, wait a minute. When you take the derivative of sine, you get, oh, we're taking the derivative, sorry. I'm getting myself mixed up with the anti-differentiation. So yes, the derivative of cosine is negative sine. Apologize for my thinking here. I've got messages coming in right and left, and they're... Okay, in number 8, a tank contains 50 liters of oil at time t equal 4 hours. Oil is being pumped into the tank at a rate. So R of t is the rate at which oil is being pumped into the tank. R of t is liters per hour. R of t is given in the table above. Use a right Riemann sum with 3 subintervals and data from the table. So remember, with Riemann sums, the main thing you got to remember is, are the subintervals equal or unequal? So 7 to 4 is 3, 7 to 12 is 5, 12 to 15 is 3. So we do not have equal subintervals, so the bases are going to be different. So for the first, you can see the work. So when you do that Riemann sum, you got to remember there was an initial condition of 50. That would be an easy thing to forget, and I'm sure that the answer without the 50 is there. So then you're going to have the Riemann sum, so first rectangle, second rectangle, third rectangle, and also make sure. So again, you're going to do the arithmetic and find your answer for that one. So I don't know where I was, but I had to pause because lots of noises were happening in my home. Number 9, let f be the function defined above. For what value of k is f continuous? And so the first thing you notice is that we have a common factor of x minus 2, which can divide out. We're going to substitute in the 2. There's going to be a hole in the graph here, but we're going to try to figure out where that hole occurs, and it occurs at 5. We're going to substitute 2 for k, and we get k. And we're going to set the y values equal to each other, because for the function to be continuous, that the x value has to generate the same y value on both pieces. And as you can see below, the 3 conditions of continuity are there, and you can read those on your own. You don't need me to read them to you. Number 10, what is the area of the region in the first quadrant? Most of these are really about reading carefully, that they only want the first quadrant bounded by e to the x over 2. Now, some people may be nervous about what does that look like. Well, you can baby graph that thing, substitute in some numbers. Hopefully you know that it's exponential. I substituted 0 here and plotted that point. Then they also are bounding by the line x equal to 2, so just remember that that's a vertical line. So the region that they're trying to get us to find the area of is here. So that's from 0 to 2, top minus bottom. which the bottom is 0. But then when you're going to do this anti-differentiation, you need a u substitution. So we're going to let u equal to the power. The derivative of that is 1/2. There's no 2 in the integral over here, so we're going to multiply it to the other side. The other thing that we have mentioned in another video, don't forget to change the bounds into u bounds. Don't leave the 0 and the 2. You got to change those into u bounds by substituting here. All right, let's go on to the next one. Number 11, we have the square root of the absolute value of a function. So normally, we can't take the square root of a negative number. That's not normally. But here we're taking the absolute value of any number that we substitute in. So instead of having just this side of the function, which is what we would normally get if we had the square root of x minus 2 without the absolute value, we actually have the other side because we can substitute numbers now that are to the left of 2. So this is really, I mean, if you baby graph, it's not hard, but you just have to think about what's happening with the graph, and you can substitute numbers to do that. And then you're going to look at your choices, and because of the sharp turn, and which would cause a vertical tangent, the function is continuous. There is a y value, but there is no derivative at x equal to 2. Number 12, they're telling you straight up, they've already defined u is equal to the square root of x. So you're going to do the du, take the derivative of that, multiply the 2 to the left-hand side, make your substitutions, and you're not actually evaluating this, but what's going to get a lot of people on this one is what I've already talked about, is you have to change the x bounds into u bounds. So a lot of people would pick letter B because they would not change the 1 and the 4. Number 13, we have another piecewise function. For what is the value from 1 to 5 of f of x dx? If you have a piecewise function and you have to integrate, you integrate in pieces. So we integrate the first piece of 2 for anything that is less than 3. So we go from 1 to 3, integrating 2, and that's going to just generate a rectangle. And then we go from 3 to 5, integrating x minus 1. And you can see my setup down here. You can see my integration and my work here. It's really not a bad problem if you understand how to break up the piecewise. Whoops, back to 14. In number 14, we have f as an original function and g as original function. The derivative of f of g of x. Well, we need the chain rule. So the way that I did this problem is that I actually generated f of g of x by substituting g, 3x minus 2, in place of x in my function. And so that's what I did right here. And then I squared that binomial, square the first, double the product, square the last. And that's what I did here. And then I combined like terms, and then I took the derivative. Now the derivative requires a chain rule, so I have the 1/2 power in front, decrease the power by 1, leave the inside alone, take the derivative of the inside. You could have done this by taking the derivative of f of g of x, making it f prime of g of x times g prime of x, and you could have done the problem that way also. Number 15, we have an original function f. It is differentiable, therefore f is continuous. H is defined to be the integral of f of t, so by FTC part 2, h prime is equal to f. So when we see this graph as f, we can also see it as h prime, and we're putting these numbers in order. So, and we're comparing h original to h prime to second derivative. Since this is h prime, we can see that h prime, let me get my pen back here, we can see that h prime of 6 is 0, so we know that. We can see that the first derivative of h is, oops, let's clear that. No, that's what I want. Let's clear it again. We can see the first derivative of h right here is increasing at 6.